My name is Leonard Kleinrock. I'm chairman of the Computer Science Department at UCLA. We have here a really exciting and dynamic environment. And one of the activities that contributes to that environment and that excitement is the constant flow of visitors who come and spend time with us and interact with our faculty and student body. Each year, we select a few from among the very best researchers in the field and ask them to participate in our distinguished lecture series. The high point of their visit is the presentation of a lecture to our faculty and student body. And at that lecture, they present the state of the art in their field of specialty. They describe the research results, the open problems, and the directions in which the field is likely to go. And as you might expect, these lectures always generate a great deal of enthusiasm and interaction. I'm really pleased you have chosen to join us today. Let's go inside. The lecture's about to begin.
Welcome everyone to the first of our distinguished lectures in this 93-94 season, academic season. It's good to see you all again. Some similar faces, lots of new ones, lots of enthusiasm. And we're going to begin with a bang. We've got some really exciting presentations this year, and Bill Dally is clearly one of the highlights. Before we begin, I'd like to take this opportunity, this rare opportunity, to introduce a visitor who's here today. He's conducting a site visit. You've all heard of ARPA. Who's not heard of ARPA? Good, because those people will be ejected immediately. ARPA probably pays the salary of 80% of the people looking at me right now. The man who runs much of that office and contributes much of the thinking, the foresight, and the wisdom is Brian Besch, Lieutenant Brian Besch. He's here with us today. Brian, please stand up. But Brian has really provided a long, stable funding and the direction and insight to a lot of the things that you people are involved with now, whether or not you know it. Welcome, Brian. Today, we have as our distinguished lecturer, Bill Dally, and as is my wont and your sufferance, I will introduce him at length. Again, trying to get to what's behind the background of the individual that achieves such success as he has, the things that motivated him, the things in his background that brought him to where he is today. Not surprising, he grew up in an environment where science was important, and it was well supported. His father was a professor of mechanical engineering, his background having been an applied physicist. Bill was born in New York City. They could stand for about 2 years and moved to Chicago, where he grew up as a teenager. As a result of his father's influence, he was heavily involved in mechanical science, and as a young man, managed to decompose, dismount, and rebuild automobiles down to the pistons and the valves and the rings and the oil pans and all the rest. So he's an automobile aficionado par excellence. But at the age of 11, they moved to University of Maryland, and his interest in mechanical, whereas it persisted, was soon superseded when, while he was in high school, he saw an ad for an electronic technician and took a job in the Washington, D.C. area. This was 1976. This was a company building microprocessors, 1976, much of this, using the Intel 8008. His experience there is what nailed him into computers. That was the gotcha in his life. Okay, the exposure to those early design questions. He was busy punching hexadecimal digits into EEPROMs, whose maximum capacity was 256 bytes at that time. He learned on the job with no previous experience. He didn't need a degree from any place to do it. He worked there the following 2 summers, moved up to the advanced microprocessor, the 8080, doing systems level programming. And it was a very simple operating system at the time. You are looking at a high school dropout. He took all the science courses and all the things he wanted before he graduated, and he stopped. And he then had the foresight to apply to university and ask them, would you accept me without a high school degree? And of course the answer was an immediate no. An immediate no from the low-level administrators. But on the letterhead that came back with a no was the name of the guy above the guy who said no. So he wrote to the director of admissions, the manager accepted, at every place he applied without the high school degree. He selected Virginia Polytechnic Institute, which is a state school, close to home, reasonably high in ranking. He went there for a Bachelor of Science Electrical Engineering, focused on computer design, and halfway through his college experience, he sent his records back to high school and said, do I have enough now to get a high school degree? And he got it. So he's no longer a high school dropout. Continued work for that same company in Washington, D.C. He drew up schematics. They would develop the boards, send them back to Bill for him to debug in his dormitory room on campus. His room was better equipped than most of the college laboratories at the time. He met his wife in calculus class at BPI as a freshman. He married her 5 years later. As I told him earlier, she probably finally solved the multiple integral I gave her in calculus class. He found it was fun to be an undergraduate. By the way, it's also fun to be a graduate student, as I told you before. But he wished he knew now what he was back there then, so he couldn't do all the things wrong that he claims he did, but he didn't tell me what they were. Upon graduating, he got an offer from Bell Laboratories to join their OYOP program, which is 1 year on campus, basically fully funded to go to college. And he went to New Jersey for the first summer to do essentially a no-op job, just to get familiar with what was going on. They were going to give him a no-op job, but he insisted on a relevant job. And he was busy doing work on a 4-bit slice components for mini-computers, the AMD 2900. And he started to emulate the first 32-bit microprocessor. He got it emulated by the end of the summer, running at a really impressive 4 MIPS. This is 1980. Simple instructions, nevertheless 4 MIPS. For graduate degree, he went to Stanford. He went to Stanford, and in 9 months, he moved so quickly they wanted him to graduate with a master's degree, and he didn't want to. He said, don't graduate me. The reason was his wife was due to finish in September. This was only May. He didn't want to go back to New Jersey, God and spot of the earth, on his own. Well, Stanford, being afraid of Bell Labs, said no. He had to graduate. They forced him out. He went back to New Jersey. Got his MS. At Bell, he did some more microprocessor testing via simulation of the chip he had emulated earlier. At that point, Bill began to think about a lifelong career. So he considered going into business, the other world, the dark side of our career. He went to Washington to do some contract engineering for the government. After 1 year of doing so-so, noticing that his interest really wasn't on the business side, he decided to rethink what he wanted out of life. So he sent applications to graduate school for a PhD. He was admitted basically everywhere he applied at one brilliant school that made a non-brilliant decision, MIT. They chose not to admit him. At that point, he went to Caltech, because VLSI was a very hot area there, and Caltech was the mecca of VLSI work. He talked to Carver Mead, and Carver basically attracted Bill to Caltech. That's an example of good recruiting, if you will. Except Carver was busy moving into neural networks and out of digital VLSI. So he went to work for Randy Bryant doing some CAD work. Bryant left. So for Bryant, Bill built a machine doing switch-level simulation. When Randy left and went to CMU, now Bill was left hanging. Okay, Carver Mead was doing one thing, Bryant had left, so he began to talk to Chuck Seitz. This was right after Chuck had said publicly he'd accept no more graduate students. Well, he accepted them. The cosmic cube had just been built. It was thought it was clear that the interconnect needed faster switches and better switching modes. And Bill disagreed with that thinking. He looked up a particular paper I'd written on cut-through routing one time. He changed it to wormhole routing, which is so prevalent today. He eliminated some buffering problems, introduced some hard deadlock and live lock problems and solved them. Notice that the problem of narrow bandwidth channels didn't go away. So he pushed for low-dimensional nets as opposed to the high-dimensional nets that were being built by Chuck Seitz and Hypercube. That led to his design and implementation of the Taurus routing chip in 1985. He designed that chip in 2 months, and 2 months more to fabricate it. While married, while a student, in his spare time, designed this basically groundbreaking chip. In November 85, it was demonstrated, it worked well, and convinced Chuck, Site, that this was really effective technology. So they went to Intel, Chuck and he, and said, do something with it. And Intel said, we have high-dimensional chips, we have basically hypercubes, we're going to stick with that. Meanwhile, Bill was busy writing his thesis. And it wasn't on these novel ideas. He was writing on programming language for concurrent small-talk language. He was writing about how to write parallel programs with doing object programming with a variety of tricks in that domain. But somewhere deep in Chapter 5, in Section 5.2, he was describing how to build a machine to run this stuff. He was forced to put that in his dissertation, and that particular section is all that's remembered of his dissertation. Okay? He didn't realize how important it was. He wanted to stay at Caltech, but instead he took a position at MIT in 1986 as assistant professor. His feeling is it's good to go to a hostile environment, and he found one. Especially after finishing degree. He found there was a sink or swim environment. He showed up in his office. They had no office for him. They forgot they had hired him. He had to fight to get lab space. And so he got some senior graduate students. He found that senior graduate students had priority over lowly assistant professors. And he commented he feels that's the case in many universities. We might comment on that later. Okay. He began to work with Arvin on data flow. He refers to that as constructive confrontation of ideas. He learned to raise money, recruit students, started a project to build an experimental parallel machine, namely Chapter 5, Section 5.2, led to the Jelly Bean machine, otherwise known as J machine, basically made out of small commodity components, single chips. And he built it up, as he says, from the sand as in silicon. Okay? The 4 enthusiastic graduate students, plus Bill, plus funding, in August 88, they began, and they had a working machine in June 91. Customized chip with Intel supplying the chip. Now there's 3 of these machines around, a 1,000-node machine at MIT, and 2 512 machines at Argonne and Caltech. His feeling is, hardware is very easy. That's because it's easy for you. Software for a stand-up machine is really hard. Trick is to keep it simple and structured. He hates large microkernels. Feels he can make a microkernel in 5 kilobytes as part of the operating systems. You don't need the full TCP/IP protocol stack in the microkernel. He wanted to take these ideas and have industry pick up on them. Intel again said no. They were stuck on the Cosmic Cube. He spoke to Cray, convinced them, and the result was a T3D machine they announced just a few months ago. That's basically based on his chip. It's a 3D mesh net, which is commercially available, built on the DEC Alpha chip. One thing Cray had to do was negate basically the memory mechanisms that were built in the Alpha chip and create their own mechanisms to implement the technology that Bill was developing. Finally, Intel caved in, and the Paragon, of course, is low-dimensional, 2-dimensional mesh chip. Now, we're almost up to the present. We're about up to last August when an interesting event occurred. As a good citizen, Bill joined the government advisory committee. He was on it, and by the way, while at Stanford, he learned to fly 13 years ago. Big mistake. Okay. He was flying his own plane down to the commander-in-chief of the Atlantic Fleet. He was flying to Norfolk. As he crossed the landfall in Connecticut, he was out over the Connecticut coastline. He noticed that some of his gauges were pinning, and he found the engine seized up, and he lost all vacuum. So everything else collapsed as well. There was a 400-foot ceiling. He was going on instrument flight boards. They had sent him out over the sea to come back into land. There he was out over the sea, and the engine collapses. Okay. The gyros went and all the rest. The first thing he did, as a good engineer, he made a computation. I mean, the plane is crashing, and he's computing when he's going to crash. Okay. He's 8 miles out, 3,000 feet high, and at the rate he was going, he could gain 2 miles. These are nautical miles. 2 miles horizontal for every 1,000 feet of height. You do the computation, figure out where he's going to crash. It was 2 miles out at sea. He crashed 2 miles out at sea. Okay. Hit the sea at 70 miles an hour. In the next micro-inch, he was at 0 miles an hour. He didn't have a shoulder harness on. Smashed his nose. against what amounts to the steering wheel, broke it, his nose, and tore his nose, and now the cockpit began to fill up with water. Okay? So he unstrapped the seatbelt, right? And he was actually didn't realize he was hanging vertical, and he fell up against the nose of the plane again, broke the window, swam out the window. He's underwater now, fighting for his life, and he's up. I left my power book back in the plane, and it's not backed up. Decided to leave the power book and save something else. Surfaced, took off his shoes and his jacket, realized there was no land around, started swimming to a buoy. 20 minutes later, he was making no progress because there was a 4-mile current against him. He started swimming orthogonal to that toward the shore. Coast Guard was out, they shouted, they didn't hear him. A sailboat heard him, picked him up, brought him to land, emergency hospital, stitched the nose, bought some clothes, new glasses, on a flight, down to finish the meeting. Days later, he went and really got himself stitched up properly. That's the kind of guy we're talking about. Things is up today. He has a message for you. The message is this. Follow your ideas through to a working system. Ideas should not get uninteresting after the first paper is written. New, significant, unusual things arise when you implement. Bill, tell us all about it.
Do we have any time left for that? Well, now that I've been thoroughly embarrassed, I'd like to tell you about some projects we've been working on at MIT. And what I'm going to tell you about, I don't want you to think about as a talk on parallel computing. I want you to think about it as a talk on computing. And I'm going to start out by showing you some pictures of some experimental machine work we've done at MIT, and then move from that into some slides talking about what is pushing the industry in a compelling direction that's going to make everything, all computing, parallel. And it's really the confluence of 3 technologies. The driver is integrated circuit technology, which is making it economical to build parallel machines and making almost any other way of pulling performance out of computing hardware very uneconomical and very unattractive. But it takes more than raw circuits to build an effective machine. It takes the appropriate set of hardware and software mechanisms working together to take the circuit technology and focus it on the problems of interest. And it's not one or the other one of those in isolation that can do the job. It's really a combination of both. So I'm going to discuss some trends in circuit technology and then how some ideas in architecture and software working together have firmed up to make it possible for people to apply parallel computers, not just to grand challenge problems, but to problems of all sizes. Try to give a little bit of a vision of the world in the future in which all computers are going to be parallel. Let's start with the picture show. During my long introduction, Len mentioned the J-Machine. The J-Machine is a project we started with a vision that the commodity chip that people make today is not as useful as one could define a commodity chip to be. First of all, I should dispel this myth about processors being commodity chips. The definition of a commodity chip is that it's sourced by multiple vendors in large volume and sells at a small fraction above its manufacturing cost. Other than single chip microcontrollers, things like 6502s and 8048s, there aren't any processors for which that statement holds true. Alpha chips are not commodity chips. MIPS R4000s and Sparks are not commodity chips. They sell at a large multiple over their manufacturing cost, and they are often single sourced. We envisioned a commodity chip as being one that was mostly memory and had this little processor down in the corner to add value to it and had an interconnection network hooked up to it. We looked at what we could practically build, and we couldn't quite build that, but we could build a good prototype of it. So we got 4 enthusiastic graduate students together, and with some help from Intel Corporation, built the chip that you see here. It has a large amount of memory on it. There's 18 kbytes of memory, organized in 4,036-bit words. It has a processor, which is this little thing down in the corner here. And then a lot of the other logic is the glue that connects things together. What we're experimenting with in the J-Machine is providing end-to-end support for communication and synchronization between nodes, that a user-level process on one node can send a message to another node with no operating system intervention with full protection. So that's done through a translation process. This big unit over here is what we call the address arithmetic unit, and it manages a translation buffer, which is mapped into the same RAM as is used for local storage, since we wanted to limit the complexity of the chip. And I think that people often get frightened away from doing custom VLSI. This chip involved about 8 man-years of graduate student effort. I don't know what that translates to into engineer and industry effort, maybe 16 man-years. But it's certainly a relatively easy task compared to, for example, building the programming system to run on. this machine. We take these chips, and the contrast on this slide isn't good, but this shows you a node of the machine. And one idea I'll stress in the less specific part of the talk is that of physical granularity. You'll see many machines today are starting to get fat and cumbersome. And what they're really doing is taking a whole lot of workstations and packaging them together in one cabinet and giving you a quantity discount, right? You can buy Sparks from Sun for $5,000 a piece, or you can buy them from Thinking Machines, and with the quantity discount, they're only $30,000 a piece. And in fact, many people are even taking these nodes and growing them up larger than the workstation nodes in terms of memory. Because memory is really what you grow when you grow a node. The processors are really very small things. Remember that little thing down in the corner of a chip. The node we built here has this single chip, the die photo you just saw, which includes a 32-bit RISC processor, 18 kbytes of memory, and a three-dimensional mesh router, and then 3 external 4 megabit DRAMs that provide a megabyte of memory along with synchronization tags and error correction. So this one piece of circuit board, which measures 2 inches by 2.5 inches, is a processing node of a parallel computer. You can take 64 of these, and this is your single board computer. Think of it as a workstation. An 8x8 array of these. You can take a few more and stick them in the box with one of the proud graduate students standing behind it. And this box, which takes up a floor space of approximately 3 feet by 3 feet, contains a 1024 node J machine. This is the one in daily operation at MIT, available over the internet as marmaladedai.mit.edu. And it contains 1024 processing nodes and a gigabyte of memory in the upper part of the electronics bay. It has a number of peripheral cards in the lower part of the electronics bay. And it has 80 disk drives in the base of this cabinet that are used for a parallel file store. Let me show you the internals of this. This is the electronics bay. At the top we have the processor stack. This is 16 processor boards. There's a 3D interconnect that we developed for this machine that ties them together. You see the tie rods going through the middle of the machine. In between each board are a number of elastomeric connectors. Think of these as little pieces of rubber that conduct electricity one way but not the other way. It's an anisotropic conductor, and they connect from gold pads on one board to gold pads on the board below. And there are approximately 2,100 vertical interconnects between adjacent boards in this machine. So the bisection bandwidth of this network is on the order of 3 gigabytes per second. And in fact, the fast direction is the vertical one, because those wires tend to be shorter than the horizontal wires, which cross the gap in the middle of the machine lines with wires as long as 4 inches. So here we have our 16 board stack. Each board has 64 processors, 64 megabytes of memory. Each of these processors can communicate. It can read and write out of its own local memory, both the on-chip and the off-chip. It can communicate with its north, south, west, east, up, and down neighbors. And the network, of course, is wormhole routed 1 clock per hop. The clock in the network is 32 megahertz. Although I think the machines we have installed at Argonne and Caltech, we have run at a 28 megahertz clock. It makes the phone ring less often to do that. They have not had, aside from one connector problem at Caltech, they have not had a single hardware problem with their machine. There's another view of the processor stack. Okay, here's the front disk bay partially populated. There's room for 80 disks here. 40 go in this front bay, and then there's a rear bay that takes an additional 40. The disks are packaged on circuit board-like aluminum plates, 4 per plate, and they cable together locally on this plate. That makes up one SCSI string that goes to a controller. And one nice thing about building a high bandwidth network, and sort of one general engineering principle, is solve each problem you have in a system design once, solve it very well, and then use that for everything. And the problem here is one of communications, whether it's communications for I/O or communications for interprocessor messaging and remote procedure call. We solved that communication problem and solved it once, and we use it for all of the I/O as well. Here's our dual disk controller board. It turns out that these network channels that when you run it at 32 megahertz are something in excess of 32 megabytes per second, because it's a 9-bit wide channel. 2 of those channels come in on this connector. Turns out our message-driven processor chip is the ideal I/O controller, since it's the one thing that is readily available that talks to this channel. And then we simply memory map peripherals, so we have a dual-ported memory and a standard SCSI controller memory map into the address space of that node. And this is the basis of our disk array. You can, although at this point in time we're simply running a standard block structured file system, you can take all of the various redundancy schemes on arrays of disks and implement them in software on top of this. The network bandwidth here is order of 32 megabytes per second. The SCSI string rarely exceeds 5. In fact, I think it's almost a guaranteed not to exceed speed for transfers over that. So the I/O load on the network winds up being very low. You can communicate from any node in the machine to any disk in the disk array, and the network bandwidth is not the limiting factor. We have a couple other interesting peripheral boards we made. This is a dual distributed frame buffer board that's used for graphics. Again, we packaged 2 on one board simply due to form factor constraints. And each of these MBPs has its memory dual ported. In addition to the standard DRAM, it has some VRAM that you need a minimum of 4 of these nodes, 2 of the boards, to refresh a screen. And again, it's set up so that the interconnection network is not the bandwidth limit, so that any processor in the entire array can paint any pixel on the screen. And the bandwidth rates are sufficient for real-time animation. Then, of course, there's the board. This is our S-Bus interface board that connects you to the host so you can talk to the rest of the world. Well, enough for the picture show. The reason we built the J machine, and I think the motivation behind a lot of computer systems research, not just hardware research, in the academic world, is we wanted to explore what directions technology was pushing us. When I say technology, I don't just mean fabrication technology, I mean also architecture and software technology. And we wanted to explore it in a way that most people in industry can't afford to do. We can go out in an academic project and try lots of crazy ideas. Of course, we never think they're crazy at the time. And if some of them don't work and our project is delayed by a year or our project fails, it's not the end of the world. Graduate students take a little bit longer to graduate, or in fact, maybe they write a great thesis about why something didn't work, which can actually wind up being more of a contribution than saying why something did. Whereas people in industry are very conservative. They make small increments over what they did last time, because if they're a year late, their competitor takes the market away, and they're out looking for another job. So let's look at some of these technology forces and how they're pushing us in the systems area to experiment with different ways of doing things. The first technology force I'm going to talk about is circuit technology. And I'll call this the case of the vanishing CPU. What happens with integrated circuit technology is approximately every 4 years, the line width of a process, so if you view this as being a transistor with the active area shown in green and the self-aligned polysilicon shown in red, the gate length, the width of this polysilicon strip, which is the length of the gate, cuts in half, as do most of the linear dimensions. In fact, recently with some of these chemical mechanical planarized processes, things have been shrinking faster than 2:1 in some of the things that count, like metal pitch. What happens when this happens is where you had one big transistor before, it sort of fissions and you get 4 little ones in about the same area. And these little transistors are about twice as fast, and you get 4 times as many of them. For years before we were velocity saturated, they were about 4 times as fast every 4 years. So what happened is, at one point in time when Gene Amdahl coined this law about balancing a MIPS of CPU performance per megabyte of memory, those 2 things were about the same size. What happened is 4 years later, you did this, the CPU got 4 times faster, so you put 4 times as much memory down, and now this memory is 4 times as large, and first approximation, 4 times as costly as the CPU. And this repeats again and again every 4 years, until eventually you get to the present state. And I challenge you to do this. Go into your office, get a screwdriver, dismantle your workstation, PC, whatever is sitting on your desk, count up the number of memory chips, count the number of other chips. For chips you're not sure about the area of, find a belt sander, sand the top of the package off. If you do this carefully, you can put it back together. And count up the amount of area devoted to processing. And by processing, I don't mean those big caches on the CPU chip. That's not processing. I mean the arithmetic units. And you'll find that it's less than 1%. We really have gotten to the point where processing is a tiny fraction of the silicon area in our machines. This has led to some side effects like sloppy CPU design. CPU designers are gratuitous in their use of silicon area. If a memory designer saw some of the things they would do, they would be appalled. So an interesting lesson that comes out of looking at this trend is that you want to balance your machines not by the ratio of speed to capacity. You want to balance them by cost. If you have a machine which 1% of the silicon area is in arithmetic performance, what if we spend 10% more on our machine and make that 10% of the silicon area? We've modestly increased the cost of our machine, and even if the utilization of that is only 20%, we'll have doubled the effective arithmetic performance of the machine for 10% investment in silicon area. And I think that this cost has gotten left out of the equation when it comes to machine balance for too many years. And the sort of current trend toward emphasizing benchmarks stresses that, because remember, benchmarks were written for yesterday's machines. For a while, it was benchmarks measured how well you were making a VAX, because all the benchmarks were made to run on a VAX. You need to do is look at the applications and how well they benefit from it. Another thing that's happening is at one point in time, you could be a pretty good system designer by being a good reader. You would call up the local manufacturer's representatives and have them send you piles and piles of data books. And you would read what was in all of these data books. And after a while, you read these data books, you don't need any formal education. You could just plug all of this stuff together. But that area is gone. For any electronic subsystem produced in any volume at all, well-defined any volume at all, it's more than 100 units a month. Standard off-the-shelf parts are out. If you want to be economically competitive, you build custom integrated circuits of one form or another. System design today is on the chip. It's not economically feasible to build systems in volume any other way. What's happening is that these chips are gobbling up the world. If you take that growth rate of 4 to 1 in terms of what you can get in a given area, and couple that with the fact that the dies are getting larger as well at a significant rate per year, you can say that in 1993, in a 0.8 micron technology, you get about 1.5 billion lambda squared, where lambda is a half a gate length, the unit of area, on a chip. It's two lambda is the width of that, the length of that gate. In 97, it goes up by a factor of 6 to about 10 billion. 4 of that is from shrinking the line width. The other 2 of the 6 is from die already getting larger. And by the year 2001, HAL will be built out of chips that are 60 billion lambda squared in area. To give you perspective of what this means in real units, a DRAM bit takes about 100 lambda squared. A full-fledged floating point unit is about 200 million lambda squared of area. So that what you can do right now is you can take, in 1993, about 8 full floating point units. And if you put no registers, no memory, no anything else about them, you can plop those all down on one chip. So floating point units aren't very costly. They're about 1/8 of a chip. So here's the situation in 1993. You have a floating point unit, a RISC core, and today about the only thing people have figured out to do with the rest of this chip area, other than put their name in large metal letters, is to put memory down on it. Gordon Moore at a conference on VLSI back in the 70s said, as far as VLSI goes, I haven't seen anything interesting to do with this technology other than make memory. And we're proving him right, which I think is a real failing on the part of architects. Well, one vision of the world is that we'll simply go to this 1997 chip and we'll have bigger caches and bigger TLBs and more buffers of various varieties on our chips. There's another thing that comes out of this, is that there's this view today, which I think is very misguided, that if you want to build a machine, you have to use one of these mythical commodity CPUs that's out there. And I think this is misguided for 2 reasons. One is that designing this part of the chip, the arithmetic part, is actually very simple. People have really understood how to build arithmetic units and register files and sequencers for many years, and at one point in time, a lot of graduate students got PhDs for adding instructions, and then at another point in time, a lot of graduate students got PhDs for taking them out. This is really a fairly simple part of the overall chip design. Part of the chip design that's hard is designing the memory subsystem, designing the memory interfaces. And that now has been largely absorbed onto the chip. First, in many cases, second-level cache memories are on the chip, the memory management structures are on the chip, and the first-level system bus interface is on that chip. And if you don't control the chip design, you are a clone maker. And that is a commodity business. You can buy various clones of IBM PCs from different people for a very small margin, 10 to 20% is typical over their manufacturing cost. It's a cutthroat business because there's very little intellectual value added. It's a manufacturing business. That's what people are going to be doing if they insist on buying chips from other people, because the system design is on the chip. And that's where the intellectual value added is. The other side of the chip world is memory. And when we wanted to do the J-Machine project, we were very interested in putting a DRAM on the chip. We didn't have the resources to do that in our engineering staff. Chuck Seitz at Caltech has built a chip with some similar and some different goals, and he's done a superb job of integrating DRAM onto a single chip node. But for the time being, most people who build systems buy DRAM from DRAM manufacturers, almost all of which are not on this continent. And what I've plotted here are 2 lines. And if I plotted this on a semi-log scale, you wouldn't get the point. So I plotted it out on a linear scale. This is the capacity of the chip in megabits, going up exponentially. And this is bandwidth trends that I've extrapolated out. Conventional asynchronous DRAM chips, which is what you find in almost all computers today, even if you get them 16 bits wide, which have only just become available, have about 80 megabytes per second maximum bandwidth out of the chip. One interesting parameter measure on a memory system or a memory chip is to divide this line by this line, and that gives you a capacity to bandwidth ratio, which you can think of as a time constant. It's how long, if you take the chip and hold it upside down and shake it, it takes all the bits to come out. So it was, a 100th of a second in '89. It's going to hit, roughly 1 second in 1998. People have tried to hold off this crisis in bandwidth by going to better DRAM interfaces, sync DRAMs, and a startup company in the Bay Area has produced something called Rambus. And these interfaces push from the 80 megabytes per second up to a little bit better than 200 and up to 500 megabytes per second. But one way to think about that is going from conventional to synchronous DRAM keeps the wolf from the door for about 3 years. The capacity to bandwidth ratio is changing fast enough that you can play this better interface card once, and then 3 years later you're right back where you were. So one aspect of this technology trend on system designers is that system design is on chip, and it's also on the memory chip, because the big problem in system design is bandwidth. And if you don't have bandwidth out of your memory, you've got a problem. And what this is saying is that unless you have an enormous capacity memory, you're going to be buying your memory not for the number of bits that memory chip has, but for the number of bits per second it's going to provide to you. In the short term, this is going to lead people to not just settle for sync DRAMs or Rambus chips, but they're going to do their own custom interfaces on a RAM chip. And unfortunately, you're going to need a very large volume. I imagine you need 1 million units a year of a particular chip type to convince a offshore DRAM manufacturer to customize that chip for you. In the long term, the CPU is going on the DRAM chip, because MCMs and all that are great technology, and they'll double the pin out of a chip. But we're not talking about a problem that doubling will fix. The pitch on this, metal pitch on a 0.8 micron chip today is about 2.5 microns. It's getting down to the point where processes that are going to come online in 3 or 4 years are going to have 1 micron metal pitches. On a chip that's close to 2 centimeters across, it means there are 20,000 metal lines going across that chip. That's a lot of bandwidth you have locally on chip. You're not going to get with MCMs or anything else that kind of bandwidth off this chip periphery. The bandwidth problem is only going to be solved by integrating the processors and memories on chip. And that will happen probably about the time people hit 256 megabit chips. So that's the direction circuit technology is pushing us. VLSI chips are gobbling up the system. They're gobbling it up to the point where we're very close to seeing systems in which there are 2 chips. There's the processor up in the little corner, cache memory interface chip, and DRAM chips that connect to it. And not too far out in the future, the gobbling is going to continue, and that's going to all be absorbed on 1 chip. So that's a driver. That enables a lot of things. It pushes us in different directions. The 2 things that can use that driver to actually solve problems are architecture technology and software technology. For architecture, I'll talk about a few things. One of them, which is very near and dear to me, is interconnection networks. Interconnection networks for parallel computers was at one point in time an exercise in topology. That's largely changed. It's now an exercise in engineering to keep wires busy. Because the constraints you have is you have a bunch of processors and memories you want to hook together somehow. They have demands in terms of message lengths and bit rates between pairs of nodes. And then you have a constraint in terms of what packaging technology is available to you. And there are usually 2 constraints here. One is a wire density constraint. How many wires can I run across the middle of my machine? And one is a pin constraint. How many pins can I put on my chip or on my module? And rather than sort of looking at abstract mathematical properties of topologies, today a system designer looks at the topology and says, how can I keep all of these wires busy doing productive things? And how can I keep all of these pins busy doing productive things? Because if I do those 2 things, then to a first approximation, I'm not going to get any more bandwidth out of this network no matter what I do. And the lesson here is to figure topology into packaging. And that's, when I made an observation at Caltech when we were building hypercube machines, that gee, we had to build 2-dimensional mesh machines. It was basically, using the basic first principle of queuing theory, which is that you'd rather have 1 big server than a lot of little servers. And with 1 big server, which is basically fat channels, but fewer of them they could share in a low-dimensional mesh structure as opposed to a lot of dedicated but narrow channels. In a hypercube, you wind up with better bandwidth utilization as well as lower latency because you're physically conservative in your communication. Your bits are taking Manhattan shortest paths from source to destination rather than going through some logarithmic network which is taking them all around the block to get next door. The single fundamental thing which distinguishes a massively parallel processor, or any parallel processor for that reason, from more conventional views for example, the vector parallel processors that Cray has built for years, is illustrated in this graph. If you look at a Cray C90 parallel vector computer, it has 32 vector pipes. That's probably as parallel as most machines that Intel and Thinking Machines ship. They scale up larger, but most of their machines are in that range. And in fact, when you start looking at the pipeline depth of those pipes, it's a very parallel machine. The reason it's also a very expensive machine is that if I plot bandwidth as a function of sort of neighborhood size or region of memory I'm talking to, for C90 it's flat. I can talk from any vector pipe in that machine to any location in its memory and get a bandwidth of 1.5 words per arithmetic operation. That's an interesting ratio. It's the global bandwidth to arithmetic operation. In a massively parallel processor, like, for example, the Cray T3D or the J machine, what you find is you have very good bandwidth to your local memory. In fact, usually better than what you could have afforded to put in a machine where you had a flat memory bandwidth. But it drops off as you go sort of one radius out. In fact, unless you're packaging your machine in a very sparse way, it has to drop off with the 2/3 power of the number of nodes, because you're facing an area versus volume problem here, and it's hard to beat physics. So as you build your machine larger, this bandwidth drops off. And that is an opportunity, because most programs have locality properties. People have taken advantage of this for years to use cache memories. You can use the same locality properties to make most of your memory references in the cheap part of the bandwidth, and to use few of them where the bandwidth is sparse. So the key idea here is don't try to spend lots of money putting bandwidth where it's expensive. Grab the bandwidth where it's cheap and use it effectively. So that's one part of architecture technology. And communications is clearly the limiting performance factor for most parallel machines. If you look at machines I think that have done a good job on that, a Cray T3D, for example, has a bandwidth ratio of a memory access to the local memory versus a memory access across the diameter of the machine. The bandwidth ratio in bits per second sustainable is a 10-to-1 ratio. The latency ratio is less than 2-to-1. If you look at other machines, you'll find bandwidth ratios that are 300-to-1 and latency ratios that are thousands to 1. Okay. But that's only part of it. The next thing you need to do is to have a naming structure which makes it convenient for programmers to reference objects that are around the machine. And what naming means is taking a virtual address, which anybody who programs these machines wants to be global. In other words, that address means the same thing no matter what node of the machine you're on, and it can reference words that are stored anywhere in the memory hierarchy. The memory is physically distributed, which means it has that bandwidth profile I showed you, but logically it's shared and lives in this global address space. There are lots of aspects to this, and I'm already running over after this lengthy introduction, so I'll just sort of list them here. You need to be able to map these in such a way that you can interleave your memories, that when you have a structure which is getting beat on pretty hard, you can get the benefit of the global bandwidth of the machine and not be limited to a single node. When you do this mapping, often you'll find that parts of your structure want to be used in many places, which requires replication, and to make the replication work well, you need some hardware support for coherence in that replication. A big issue here is granularity. A lot of people have tried doing this with conventional paging hardware. And the problem is that the locality of spatial locality profile of most programs falls off very rapidly, 8 or 16 words out from the reference you make. The probability of making a reference there is almost down to background level. So if you move a 4 kilobyte page across the machine every time there's a reference, most of those bytes you move will never be referenced. You've just burned up a lot of bandwidth, which is a critical resource, unnecessarily. And so what you really want to do is want to move around things which are 8 or 16 words in length. A lot of people realize this and they said, aha, those are cache lines. So what we'll do is our memory hierarchy will be from our local cache, which tends to be the small little thing, out to the rest of the machine. And our local memory is sort of sitting to the side. But that's leaving out a level of the memory hierarchy. What you really want to do is have a memory hierarchy where you move things from your cache, which you can reference in 1 to 3 cycles, to your local memory, which you can reference in, say, 20 cycles, to your global memory, which you can reference perhaps in 50 cycles, but at some bandwidth penalty. So you're using your local memory as a level of the memory hierarchy rather than bypassing it. And I think that that's something that in trying to evolve off-the-shelf processors to these classes of machines, many people have missed. KSR has actually done a particularly good job on that. The final part of architecture is, I think, nailing down the right mechanisms for communication and synchronization. One thing you have to realize is that any reference you do across the machine, and I'll define 3 types here. Read, this is where you reach across the machine, grab a piece of data and bring it back. Write and send. Send is where you send a message across the machine, usually a block of data, and when it arrives there, it causes some action to take place. And think of this as a remote process creation. All of these involve synchronization. If you're doing communication without synchronization, you're either doing synchronization and not telling somebody, or you're taking a big chance, because otherwise somebody's going to try to read the data before it's there. And I think what most people have done is that they've put these synchronization means in after the fact and in a fairly coarse-grained way, which is why barrier is the single most popular mode of synchronization in these machines. The problem with barrier is that it's a global operation and hence has amortized over all the nodes that are operating a fairly large overhead. What you really need is the ability to have very low overhead communication and synchronization, so you can afford to send small messages, have small amounts of work done in response to those messages, and synchronize in small regions of events, where you can think of a small number of these threads being a region of events. What happens when you can do low overhead synchronization is then you can pull more parallelism out of a program. A lot of people are frustrated in trying to pull parallelism out of programs today because they say, well, I can pull this out, but there are only 50 operations to do. And the overhead of doing those 50 is 5,000 operations, and therefore my speedup curves go down. If overhead was 0, speedup curves would never go down. And what you want to do, you would simply go up, you'd run out of parallelism, and they'd flatten out. You want to build a machine which comes as close to that as possible, and you can do that if you provide good end-to-end hardware support for communication and synchronization. But we're not building this hardware to sort of sit on its own. There's really a very close coupling between the parallel hardware technology and parallel software technology. In fact, you really can't do one without the other. I think a lot of people are saying today that the hardware problem is solved in parallel computing. All we need to do is work on software now. That is certainly false. I think that the hardware technology for parallel computers is not yet mature. Many of the software problems that people are beating their heads over are of artificial nature. They're working their way around artifacts of immature hardware. Let's look at 3 aspects of software technology. Say I have some program and I want to run it on my parallel machine. First thing I need to do is to extract parallelism out of the program. And this happens in a couple ways. The classical way of doing this, used by vectorizing compilers for years, is to find the loop nests in the program. This is what's been called and reinvented as data parallelism. I find a loop nest, maybe even it has a few dependencies between iterations of that loop. But if I have this synchronization on data movement, those dependencies will be resolved at runtime with very little overhead. Okay? So that gives me a certain amount of parallelism. The next thing I do is I use representations of my program that wind up exposing all of the available program. For years, we've built compilers that build control flow graphs and basic block structures and hide a lot of the available programs. Some people at IBM over the past 5 to 10 years have developed some compiler technology which exposes much more of this by showing program dependence rather than program flow. So I can take a program, for example, where I have an assignment to A, some various control blocks, and an assignment to B, and the compiler, if it represents this via control dependence and program dependence rather than control flow, will realize that this statement involving A and the statement involving B are executed under exactly the same control conditions. And the fact that one of them happens to come after and one of them comes before is simply an accident of how the programmer wrote the program. So that if there are no dependencies between them or between the intervening code, it could schedule them to run simultaneously and break those out as separate threads running on different nodes. And finally, modularity is for programmers. Compilers can do whole program analysis. And I think it's very important to try to pull this stuff out, that all the procedures be unraveled and wrapped up so that when you're finding the dependencies between these things and you're finding tasks to be scheduled in parallel, you're looking at the whole program. Because what I find happens in systems we build is that if you don't do that, the programmers will unmodularize their programs to expose this stuff. And it's much better to let them modularize the programs for all of the good software engineering reasons that improves productivity and makes the software more maintainable, and then let the compiler flatten it out rather than force the programmers to do that to get performance. And they will do it. They'll do almost anything to get performance. So we've taken our program, originally written as a serial application, we've shaken it around a lot, and we've gotten lots of parallelism extracted out of it, and we need to figure out where to put this stuff. And putting this stuff involves 2 things: putting the data in different places and putting the threads in different places. And one approach to this is if you have regular dense arrays, which perhaps account for less than 10% of the programs that are out there, that people are focusing a lot of attention on, you can do some interesting analysis of the program. For instance, if you have statements that show that variable a sub I is being used in conjunction with b of n minus I, rather than mapping A across the array this way and B across the array this way, and every time you hit the statement going like this, you map them like this. And so it just so happens that this value of A is right where the value of B needs to be. And this is actually some work that one of my current graduate students did before she came to MIT. Kathy Nove has published a number of papers on data optimization and more recently subspace optimization, which looks at the problem of placing sparse arrays. Another thing you can do is you can look at a lot of algorithms, say like FFT, that can be blocked so that you group all the data you need together for a little while, operate on that, and then regroup. So that an FFT can be basically blocked into a high radix FFT in which you do a radix, say 4 FFT, so that the communication only occurs in relatively large stages and most operations are local. And of course, the importance of coherence technology is when you have an irregular problem, what you can wind up doing is moving your threads around to load balance the problem, and letting the coherence technology, particularly if you have your memory hierarchy such that your entire memory is part of that coherence, migrate the data to where the threads are using it. And I think that you actually need both. You need the compiler-directed placement as well as the coherence to cover all the bases. I'm going backwards, no wonder it's going so slowly. The final thing is I've extracted the parallelism out of my problem, I've placed it on the machine using this neat technology. By the way, the stuff in red here is how hardware interacts with this. In many cases, you can't do these software optimizations unless the right hardware hooks are there. Or I shouldn't say you can't do these machines are all, if they had infinite tapes, Turing machines, but you can't do them efficiently. And scheduling, and I've just shown one example of it here, is basically having a model of the machine, and particularly of the network and memory delays, and being able to schedule operations so that you have the equivalent of Japanese just-in-time inventory on data. You don't want to go either way. You don't want to do the wait until I need it and ask for it, which is sort of shown on the left here, where I place a load right before I want to use it and wind up stalling the thread, perhaps for hundreds of cycles, waiting for that data to show up, being fetched across the machine. I want to put the load exactly the latency before the use. If I put the load too far before the use, I get the inventory control problems that happen with a bad inventory system. And the inventory control problem is really the question of how I manage my register space and my cache space. If I'm loading too far in advance of use, the amount of storage I need to buffer those loads goes way up. I can wind up thrashing my cache. I can wind up having tremendous register pressure, since very often the registers are actually used as a buffering for these remote loads. So I need a predictive model in the compiler so I can schedule not just loads and communication actions, but actually all operations. So what's going to happen to software? In the near term, what people are going to do is that they're going to take their sequential programs, because that's what they're comfortable with. They're going to compile it so that it extracts parallelism, places it, and schedules it. And they're going to get a little bit of parallelism out of it. But remember, if we applied 10% more hardware to our machine and had 10 times as many processors, even if we only keep 1/5 of them busy, we're ahead of where we would have been with the serial processor. So even if they get a factor of 2 speed up out of this, in other words, on the average 2 threads running at a time, they're winning, and they're winning enough to make it worthwhile. You don't need to get large process utilizations to win with parallelism. Very modest improvements will actually be quite competitive with serial. Then what they can do is they can go in, and if they're really greedy, which most programmers who want performance are, they can annotate the program and pull multiple levels of parallelism out. In many cases, rewrite things which are artificially serial. What they'll find after they've done these annotations for a little while, I'm going backwards again, is that they'll really want to have less constrained program specifications. The problem is we've developed over the years a set of program specification tools that expose far too many details of implementation. I refuse to believe that C++ is an object-oriented language. Any language for which you can go *S++ to manipulate a string is not hiding the implementation of an abstract type. And I think very often things like this, for example, if I say I want to sum an array, and I really should have done this as S equals S plus *A++. Basically hides the intent. The intent is I want to sum an array. This shows a particular operational way of summing an array. What I'd really like to say is sum this array. And if I do that, then the compiler can look at that and say, yes, we have parallel ways of doing this, and not have to take this recurrent structure and convert that into a logarithmic structure through a set of transformations. There's no sense undoing stuff that's already done, because if the programmer's thinking something, he then warps what he's thinking to fit a programming notation. It has to be warped back by the programming system. You're losing something. Similarly, if I want to enqueue something, queues wind up being points of serial contention in a lot of parallel programs. They need not be points of serial contention. There exists, developed by the NYU folks in the Ultra Computer Project, very good parallel algorithms for implementing queues that are multi-access. And if I implement the queue as an abstract data type, I can come up with those parallel algorithms and let the programmer use them without even fully understanding their implementation, rather than having him specify in a very low-level way how he wants to implement a queue that may be overly serialized. Well, let me move forward. I'm going to start to accelerate. Applications. What's important are applications, not codes. There's a very big difference between those. Applications are problems that people need to solve. And people, for example, the people in the oil companies who have big reservoir modeling problems they want to solve, are very willing to rewrite a code if they can get a 2, 3-to-1, 5-to-1 performance improvement out of it, because they're very hungry for performance. An application sets the requirements on the machine and the requirements on how you want to divide your resources between processor, memory, and communication, the three elements of all. Computers. The size of the problem you want to run sets the total amount of memory. You got to hold that problem size. The local interaction within that problem says how much local bandwidth you need. The global interaction says how much global bandwidth. And then you trade those requirements off against the cost of implementing these things, so that basically all your partial derivatives say that you're getting the same diminishing return for every dollar spent on the last bit of communication, the last bit of local bandwidth, the last bit of processing. A lot of people have been focusing recently on large problems. That's the lazy way out. What's actually hard is not to run a large problem on a parallel machine. It's to run a small problem on a parallel machine and make it go fast. And in fact, while scientists need to run these large problems to learn new things through computation science, the day-to-day engineer that adds productivity to American industry by designing a better piece of an automobile or a better piece of consumer electronics wants to run a small analysis, typically, something that can be fit in a small amount of memory, certainly less than a gigabyte. But they want that to be fast. The circuit designer would like to grab a couple knobs, like on an Evans and Sutherland picture system, turn these knobs to very device sizes and watch the waveforms change. A automotive designer doing crash simulations doesn't want to wait overnight to say, oh, the passenger died. Let's try moving this beam over here and seeing if we can save them. They like to reach out and move the beam and watch the deformation of the crash simulation result change in a 3D graphics window. And these are problems with lots of parallelism, even for very, very small size. But to get that parallelism, you've got to pull it out at the level of a few tens to hundreds of operations. You can't run 10,000 operation threads and get parallelism out of these small problems. Running small problems puts the pressure on the architect and on the programming system to make it efficient to get small problems. We also need to look at some data-intensive problems and look at the I/O problem not as the large bandwidth checkpoint that it is on most scientific machines, but rather as something more akin to transaction processing. We're moving the order of 100 bytes around. So let me state what I think is the parallel imperative, and I'll state it in terms of two graphs. The first graph here I've informally cooked together looking at a lot of recent product announcements. IBM recently announced the Power 2 version of the RS6000 architecture, where they can issue something like 6 instructions simultaneously. But if you look at how well that does on some real codes that I have around, it doesn't reach 1 instruction per clock. And in fact, if you roll back time a little bit, you can wind up for a relatively small amount of silicon area. And recall, this is a semi-log plot drawn the opposite way that most semi-log plots are. I've got cost here, area and lambda squared, on this axis logarithmically, and performance linearly. Whenever you have the semi-log plots in that direction, it means you have a problem. It means that you can do a lot in terms of spending dollars, in this case, dollars silicon, and you're not getting much back in terms of performance. Very simple single-issue RISC processors are within a factor of 2 or 3 of the best that people can squeeze out of multiple issue, very wide superscalar machines. And even those very wide superscalar machines, where they squeeze out that, they're often pulling out parallelism that you would be more efficient exploiting at the level of multiple nodes. The real instruction level parallelism isn't what you get by unrolling a loop and scheduling your superscalar processor on that loop level parallelism. That stuff should be exploited across nodes. Instruction level parallelism is what you can't exploit across nodes because it only exists in a thread size of perhaps 1 or 2 operations. And there's actually very little of that, perhaps 2 or 3-fold.
Is this a consequence of the compiler technology that is out there currently, or is it inherent in the problems that you're talking about?
I think, many people say that's a matter of opinion. I think it's inherent in the problems. If you look at what calculations need to be done in these problems, you can pull most of the parallelism that exists out at a level such that it's efficient to put it across nodes. And what's left is perhaps a factor of 2 or 3 instruction level parallelism. And that's all that these, very, say, a factor of 1,000 larger than simple machine processors are pulling out is that factor of 2 or 3. They'd be much more efficient pulling it out, pulling the other stuff out, which they're also often labeling as instruction level parallelism at the thread level. So rather than pay $1,000 to get a 2 times improvement in performance, what you really want to do, I didn't want to put this overlay on it, is you want to look at the problem as follows. Suppose I need, remember, we're driven by requirements. The application has some requirements. We've got to hold the problem. It's a gigabyte, okay? Now the question is, how much do I spend on processors? Well, it turns out that actually pretty powerful processor, one that's perhaps, this little line here is a megabyte of memory. A billion lambda squared of area, called a floating point unit, is about 200 million lambda squared of area. So a pretty big processor is about a megabyte of memory. So the first approximation, until I get down to a megabyte of memory per node, my processors are approximately free. At a megabyte of memory per node, all of a sudden I become processor dominated. My cost per node will go up linearly as I shrink that, because I'm basically paying all processor now. As I add more nodes, if I have 10 times as many nodes, it costs me 10 times as much. Let's look at what happens now. As I go to 10 times as many nodes, my local bandwidth aggregate goes up by a factor of 10. I have 10 times as many processor memory connections over which I can transfer bits. My global bandwidth goes up as a 2/3 power. It's that area to volume ratio. You can't get around that unless you want to spend lots of money, and even then, you can't cheat physics. What does this mean to cost performance? Well, what we observe happening on the J machine is a machine with very low overhead, so our speed-up curves don't droop as soon as a lot of other people's do. Cost performance goes up linearly for a while. What's happening there is your program is in a region where it's local bandwidth limited. So as you have processor nodes, gobbles up that local bandwidth, and you do linearly better. You then reach point 1, labeled a little red arrow here. At point 1, you've saturated your communication network, and you're now global bandwidth limited. But as you add processors at this point, if your overhead is low, it doesn't droop down, your performance continues to increase, and your cost is still about the same. So because you're getting more channels across the middle of the machine, you're getting more global bandwidth, and your problem's actually running faster. What you're basically doing here is you're looking at how much you're spending on bits versus how much you're spending on bits per second. And you're still winning on bits per second until one of two things happens. This dotted line is that unfortunate case where you were running a very small problem and you ran out of parallelism. When you run out of parallelism, you don't get any more. And in fact, it flattens out until you get to the point where cost goes, and it drops off as the cost goes up. Or what happens, even if you've got lots of parallelism, you reach the point where the cost starts going up linearly and your performance is only going up as a 2/3 power until you've peaked your cost performance. But this happens around a megabyte per node. And that's with a very fat floating point unit. So one way to think of this in a cartoon form is that if I want to build a machine, do I want one very fat processor and a gigabyte of memory? Remember, you look at the ratio here, is 10 to the 12th to 10 to the 8th. I've got over 100 times as much, or roughly, 3,000 times as much area in memory here as I do in processor. Or do I want to keep the same size processor and bring my processor to memory ratio more at a ratio of, say, 30 to 1. Or if I really want to optimize things, what I'll do is I'll ride down this curve a little bit. Gee, I'm going from 0.6 instructions per clock to 0.5 instructions per clock and reducing my size considerably. And at that point, I can build somewhat smaller processors, perhaps 50 million lambda squared, and keeping the same 30 to 1 ratio, build a 1,000 processor machine and actually want to get quite a bit more aggregate performance. Which machine would you buy? Well, I want to move forward, so I'm going to skip the slide on the market.
It's not a hard stop at 5:30.
Okay, that's good because it's past 5:30.
No, so take it back.
Okay. Well, since I have a captive audience, the doors are locked, aren't they? Let me talk. This is a picture of the computer market. The computer market's about a $100 billion a year market. I draw it as a pyramid because usually there's very little at the top, very few unit sales and very little revenue in comparison. What's down at the bottom? In fact, I've dropped the bottom slice of this off, which is the roughly $60 billion a year hardware market for PCs. The software market for PCs is larger than that. So this is roughly the number of units in this little wedge of it, which is scientific and engineering, which is really a bloodbath. Because whenever engineers build a system, they like to build it for other engineers. So you've got lots of people building systems for engineers, and they're slugging it out. Over here is where Big Blue tends to do most of their work, building what they call enterprise systems. The ES9000 is sort of up in the top of this range. And the AS400 probably fits down in the middle here somewhere. And you can sort of take those enterprise systems and look at how people use them, whether they're transaction systems or decision support systems, in terms of how critical it is that they remain online over long periods of time. Then there's this process control segment of the business, which has actually been largely ignored by the parallel computer marketplace. If you look at the various applications people run in these different segments, I have not run across a single one which is demanding of either CPU performance or I/O performance, which if you broke it down to a finite grain size, didn't have adequate parallelism to keep lots of processors busy. There is not, if you look at the applications, not the codes, serial bottlenecks in most of these marketplaces. What I think is going to happen is that the technology base is going to identify the targets here. When you look at what you get out of a parallel machine, remember the graph I just showed you, what you really get is for the same cost, you get more bandwidth. That bandwidth means not just arithmetic bandwidth, local memory bandwidth. It also means I/O bandwidth. And a lot of these problems, particularly at this end, are I/O intensive problems. You can benefit a lot by not trying to shovel all of the bits through the same central pipe of a typical storage controller in the center of an IBM system. I think what you have to do to hit these various markets, though, is you need to offer instant gratification. That's what most Americans are into today, right? Software, which means day one they've got to be able to take some code out of the box, and this means code, not application, and get it to at least operate on the machine. Now the model here is that you have interconnection networks so that your latency to the most remote part of memory is no worse than twice as much as it is to your own local memory. So if nothing else, they run it on one node using the global address space they have, run it across the machine, and they can address the same total amount of memory. The problem fits on one node, they run it day one. Hopefully your compiler technology is good enough to get a factor of 2 out of it. Once you've gotten the factor of 2, they're ahead of running this on a strictly serial processor, and from that point on, they can tweak it and do quite a bit better. I think the thing which will make this for most parallel machines is that most of these segments, and in particular some of the ones that all of the engineers aren't fighting over, are very cost sensitive. They want to solve the problem as economically as they can, and if they can buy a parallel machine for less than they can buy a serial machine to do the same problem, they will. Although I think that the hardware people among us, I'll count myself in there, have to realize that for most of these people, hardware is perhaps 1/10 of their computing budget. So let's talk about my vision of systems. I think that what you'll see in the near term is a node of a computer, say circa 1995, looking like this, where the processor is up in the corner, we have cache, the memory interface, and a handful of memory chips makes a node. This has a parts cost on the order of $1,000 to $2,000, so you might see it sell, if it's a commodity, it would sell for 10 to 20% over that, but these won't be commodities for a while. They'll sell for 3 to 5 times that much. But over the course of time, this will be gobbled up on one chip. So in the year 2000, you'll see these things selling for $100 to $200, or cost $100 to $200 per node, and they will be commodities, and they'll sell for a small fraction above that. So workstations in 1995, maybe 4 to 16 processors. In the year 2000, a workstation, something sitting in your desktop, will be 32 or 64 processors. And that will be how many chips in the machine as well, if not fewer. And you can scale on up to supercomputers. It'll be the same component. Perhaps at the low end, they'll have one-dimensional networks, and at the high end, they'll have 3-dimensional networks. So they have different pinouts, because that's a cost factor in manufacturing the chips. But they'll have 3D torus networks, 1 to 2D for the small ones, with virtual channels and adaptive routing and all of these wonderful network technologies. I think very importantly also that there'll be fault-tolerant networks. People want to apply these to their transaction processing problems where the machine going down for a couple minutes loses them tens of thousands of dollars. They want a network so which, if somebody trips over, something bumps into the box and the connector slides for a little bit, the machine doesn't go down. The packet error gets caught, the packet gets retransmitted, and everything continues smoothly. They probably even want online repair for many of these machines. Each of the nodes of the machine will have a small but effective set of mechanisms, where mechanisms are what tie the different processors together. I mean, everybody who builds parallel machines has processors, memory, and a network. What distinguishes them is that they have different sets of mechanisms that tie the processors and memory together over the network. So what they'll have is they'll have a global address space. Programmers have made it very clear that they don't want to have different address spaces per node and replicate the code on each node. That wastes a lot of that expensive memory. It's going to be cache coherent with a combination of hardware and software in there, because sometimes the compiler can predict where the data needs to go to be local with the threads, and sometimes it can't. What we'd like for it to be able to do is to have it predict that, but do it in a speculative way, put the data there if it's in the wrong place, have the hardware move it. because every time you do a data operation, whether it's a read, a write, or a send, you need to synchronize on that, data operations will be synchronizing. The question here is on what grain are they synchronizing? Will you have tags on every word to synchronize them? That's the model we've built into the J machine and our M machine project. Or will you synchronize on somewhat larger blocks? And these will be multi-threaded machines because what you want to do is to allow it's not keeping the processors busy that's important, it's keeping the bandwidth, the memory bandwidth and the communication bandwidth busy that's important. And so when you block on a long latency operation, you want to switch another thread in so that you can continue to generate work for those communication resources. So you'll have a model where you've got a number of processors. The processors have a bunch of threads that they're interweaving, and they're accessing memory that's physically distributed but globally shared. So let me sum up here since I'm a few minutes over schedule. In the not too distant future, you go into the computer store and you say, I want to buy a serial computer. And they say, well, let me go into the back room. And we may have a couple of those and brush the dust off of them. Because everything that will be produced from personal computers on up, if it's larger than a single chip, even some of the single chip ones in a not too distant time, will be parallel computers. This is going to happen. The technology forces are driving us in that direction. Circuit technology is giving us more things. It's not making them all that much faster. If you want to take advantage of that circuit technology to build machines and solve problems faster, you have to do it by solving problems in parallel. You're not going to be able to solve them one arithmetic operation at a time and take advantage of what the technology is giving us. It also makes sense from a cost balance point of view. We're building machines that are almost entirely memory today. To increase the fraction of cost that's applied to processors a little bit, you wind up getting very good returns on that investment, whereas if you apply that investment to making a larger cache or more memory, they're greatly diminishing returns. The driving cycle is such that circuit technology makes the hardware cost efficient. That then puts the burden on the architecture and software technology to come up with an effective set of mechanisms and a set of strategies for applying those mechanisms, where the real question is how you divide the problem between hardware and software, but the mode of operation is the same across the board. You extract parallelism from an application. This requires software techniques like analyzing loop nests to find out what loop iterations can run in parallel with one another, doing program dependence analysis of programs, doing whole program analysis. It involves hardware techniques like being able to create threads inexpensively, having low overhead communication and synchronization, having synchronization tags on words that these small threads you create can interact with one another efficiently. It's a hardware-software ballgame. Once you've extracted the parallelism, you have placement. And again, program analysis of data optimization, subspace optimization can do a pretty good job in placing regular arrays. And then you get the cache coherence to bring up the rear and place the things that you can't figure out as a programmer. Blocking I should have included in there as well. So this works around the cycle. You apply hardware technology and software technology to make this cost-efficient hardware work on some real applications. And you get a few hardy applications people for whom performance is important enough that they're going to be the pioneers who get the errors in the back and crawl over the hex core dumps. And really the thing that we found has turned people off from working on our machine is not any difficulty of programming that has to do with the machine being parallel. It's the difficulty of programming that has to do with the machine being an experimental prototype. They're used to these cushy environments with symbolic debuggers and all this other key sheeting stuff. And when they get on a machine in which, oh, it crashed, symbolic debugger, no, we've written a bunch of tools to help you grovel over this core dump and find out what happened. I mean, you didn't put your print statements in to create this log on the disk of what was happening while your program was running. And it's a different environment. I think it's actually that environment, more than it is anything fundamental about parallelism, that has held people off from using our machines in the way we envisioned that they would be used. But you wind up with these hardy people writing these applications. You get that all-important thing to convince people this is important, which is volume. So people actually start using these machines, which means more effort goes into the cost-efficient hardware design. People give up on these commodity processors since they don't really exist anymore, design the mechanisms in a tighter way, the software gets better, and the loop continues to close around on itself until eventually you have pervasive parallel computers. And I view our job as academics doing research is to put where we can do the most leverage, which is in a combination of the software and architecture technologies, to accelerate this loop. And the way we can accelerate it is not by making an iteration of the loop go any faster. It's by trying to jump ahead in terms of what mechanisms and hardware and what techniques and software we can do to make it require fewer of these iterations of the loop to get to the right place. So that rather than little incremental changes each time around this loop new generation of product, we can reduce the risk of some of these technologies to the point that the people in the commercial side will say, I couldn't have taken a chance on that, but since you did, thank you, I'll put that into my machine. And then therefore their machine can jump ahead perhaps what 2 or 3 revolutions of the incremental changes would have required. The other message I'd like to leave you with is if you have aspirations to hardware system design, I strongly advise you to get involved in chip design, because in the not too distant future, system design is going to be almost entirely on a chip. Even today, anything produced in volume at all, you look at boards you'll go down to the local computer store and buy to plug into the ISA bus of your PC. They got one big ASIC sitting on them, in a plastic quad flat pack, and maybe a little bit of bus glue, and that's it. And things are pushing even more that way when you look at what you can get on a single chip today. And it applies both at the high end, where you might pay 50 or 100 bucks to fabricate a chip sort of at the hairy end. Some of the processor manufacturers will then charge you 500 or 1,000 for that chip. But also at the low end. I have a friend who has a little company in Pasadena where he makes chips that flash those little beacons on the side of the road. And it's a 2 micron chip. He makes about 1 millimeter on a side, and he produces it in quantity for about 80 cents a piece. Chip design, and you're to the point now where you can actually get quite a bit on a chip that's 1 millimeter or 2 on a side, and made for truly jelly bean prices. So it's all on the chip. We're going to have single chip nodes by the year 2000 if the right market forces push it in that direction. And I think what we really need to do is we need to elevate the level of design. What's happened with design on the chip is that people started out and they all had to be circuit designers and device physicists to design chips. And then we abstracted away some of the device physics, and now you simply have to be a circuit designer to design the chip. So if you want to design a node of a parallel computer, can you go somewhere and say, I'd like a floating point unit? People already know how to build those, right? Will you please give me one? I'd like to plop it down here. No, you got to build your own floating point unit from scratch. And maybe I'd like an SRAM to be the cache. Can I please have one of those over here? Right, you got to build your own SRAM too. And I think what we really need to do to enable people to quickly go in and design things at the system on a chip level is get back to that point we had when you could call your local rep, and even though you were a 12-year-old kid who was just interested in flipping through the data books, convince him, make up some letterhead with systems component engineering on it, send it off, and get them to send all of the data books to you. You need those data books for things that you can put down on your own chip, and you need them so that they'll move from one technology to the other, so we can elevate the level at which we're designing these components. It won't be, a 10 or 20 man-year endeavor to knock out a new processing node. It will be the kind of thing that a handful of undergraduates can do in a term. I'll leave you with that thought.
Well,